And so our first speaker of today is Nicolai Reshetikhinn from Tsinghua University and BIMSA. And his topic is integrable systems on stratified spaces. So let us welcome our speaker.
Thank you. So I think everybody here knows what a classical integrable system is, classical Hamiltonian integrable system. But nevertheless, I'll just start with some basic recollections. So we'll start with the definition of classical Liouville integrable system, then classical superintegrable system, and we'll just remind what a stratified space is, and what is the Hamiltonian reduction. And everybody knows that you can use the Hamiltonian reduction to create more symplectic spaces from symplectic group space. But typically, these symplectic manifolds that you obtain by Hamiltonian reduction, they are not manifolds, they are stratified symplectic spaces. So then I'll focus on the Hamiltonian reduction of the cotangent bundle to a Lie group. For simplicity, a Lie group will be compact, simple Lie group, and even more, I'll focus on SU3, and then at the end on SUN. So, this is the report on joint work with these people, and it's two papers. One is just was put on the archive. The other will be hopefully put in August on the archive. So, what is a Liouville integrable system? We have a symplectic manifold, let's say 2n-dimensional, that is locally in PQ coordinates and Darboux coordinates. The symplectic form is dp/dq, so it's a manifold with closed non-degenerate symplectic form. And an integrable system is a Lagrangian fibration over some n-dimensional manifold. And again, looking forward, I should say not necessarily manifold, but a stratified space more generally. So Lagrangian fibration means that generic fiber is Lagrangian. There will be some singular fibers, and the Arnold-Liouville theorem says that for generic point on the base, the pre-image is isomorphic to a torus. If this pre-image is compact, if it's not compact, then it's the product of a torus and a plane. And on this torus, there is an affine coordinate system in which the symplectic form is d theta db, where b is a local coordinate system on the base. And so, and then if h is a pullback of some function on b, the flow lines that generate this function, Hamiltonian flow line, flow lines of the Hamiltonian vector field generated by this function, these flow lines are linear in theta coordinates. These theta coordinates are called angle coordinates, and because the evolution is linear in these coordinates, we mapped a complicated problem of solving systems of non-linear differential equations to geometric algebraic problem. We solved it. We solved the Cauchy problem for this system. So the question is, how does this all work when the point on the base is singular, and how does it all work for stratified spaces when the symplectic space is stratified and the base is stratified? Now, the Liouville integrability has a generalization. It's called superintegrability. It's not a very good term, but it's established term in the literature. Maybe it's better to call it degenerate integrability, in the sense that there is a Poisson manifold in between, which has so it's a structure on the symplectic space which consists of a fibration over a Poisson manifold and then projection to trivial Poisson manifold base P. Both psi and P are Poisson mappings. The generic fiber of C is isotropic, and generic fiber of P is the disjoint union of symplectic leaves. So that's the structure. That's a geometric structure, and it's called superintegrable system. And for such structure, again, you pick up any function that's a pullback from a function on the base, and then each fiber of C, it's an isotropic submanifold in our symplectic manifold M. If it's compact, it's isomorphic to a torus. And in local coordinates, again, these are the angle coordinates, so it's d theta dB. But there is a correction, plus the symplectic form from the corresponding symplectic leaf of P. Our point P is on this intermediate Poisson manifold P. Through this point, there is a symplectic leaf. On this symplectic leaf, there is a symplectic form omega P. And basically, that's the kind of Darboux theorem or action angle theorem or the Arnold-Liouville theorem applied for superintegrable systems. So this was first done by Nikhoroshev, student of Arnold, pupil of Arnold, I should say. So again, if H is a pullback with respect to the composition of pi and psi of a function on B to a function on M, the flow lines of the vector field, of the Hamiltonian vector field generated by H are linear in these angle coordinates. But now, because the base is k-dimensional, you have k-independent functions on B, Poisson commuting. So then, again, it's the same thing. The complicated nonlinear dynamics, if you succeed in these geometric constructions, then you don't have to solve differential equations. All you have to do is you have to construct angle variables. So the question is how it all works for singular fibers, and more general, say how the superintegrability works when all three ingredients, the symplectic manifold M, the Poisson manifold P, and the base P are not manifolds but stratified spaces. Respectively symplectic, Poisson, and since Poisson structure on B is trivial, so this is just a stratified space. So I already said this word several times, stratified space. So I'm not going to give this kind of all the details that go back to Whitney, I think. It's basically the following. You represent your space, topological space, as the union of pieces that are enumerated by a finite partially ordered set. M alpha are finite dimensional topological manifolds. So transition functions are continuous. And then the closure of alpha stratum is the union of all strata that's below alpha. So an example of stratification is, say, if G acts on M, H is a subgroup, H in the brackets is the conjugacy class of this subgroup, then the stratum corresponding to conjugacy classes have a natural poset with respect to inclusion. And so then the stratum is simply the space, the subset of points where the stabilizer of a point is in this conjugacy class of H. And then the set theoretic quotient of this stratified space is just the union of quotients. So that's So that's a stratified space. Functions on M. Again, here's the description of the sheaf of G invariant functions on M, which can be considered as smooth functions on the quotient. This example of this class of stratified spaces goes back to the paper by Schmar and Lerman about stratified symplectic spaces via Hamiltonian reduction. So if you want to have a symplectic structure on each stratum, then basically what they say is that you take your favorite manifold, do the Hamiltonian reduction, and then automatically you will get a stratified symplectic space. Okay, so I said this word Hamiltonian reduction. So this is all introduction. It will be very long introduction, kind of summary of all the tools that we need. So what is the Hamiltonian reduction? And I hope I'm not wasting my time because I see maybe one student. Okay, so there are several students here. Maybe second. Yes, that's right. There are some students. So we have a symplectic manifold, say Lie group, finite dimensional. Then when you have an action of a Lie group on a manifold, you automatically have a homomorphism from the Lie algebra to the Lie algebra of vector fields. And if the action is Hamiltonian, the action is Hamiltonian by definition if these vector fields are Hamiltonian. In other words, for each element of the Lie algebra, there is a Hamiltonian mu x such that Lie derivative of a function is the Poisson bracket with this Hamiltonian. So clearly this mu is linear in x, and that's why we can write it as the pairing between an element of the Lie algebra, dual Lie algebra, and Lie and x. And thus we have a map from mu. I knew that I'll forget something. So we have a map mu from M to G star. That's the moment map. So then M is symplectic. Assume that M is symplectic. G is the Hamiltonian Lie group that acts such that the action is Hamiltonian. So then the quotient is a Poisson manifold when it's a manifold. In our examples, this is a stratified Poisson space. So it's a stratified space with a Poisson structure on each stratum. And if O is a coadjoint orbit, we can take the pre-image of this coadjoint orbit in M. It's a quasi-tropic subspace, and then the quotient of this quasi-tropic subspace by G, it's a subspace in M mod G. Typically this is a stratified symplectic leaf. So it's called the Hamiltonian reduction of M via the orbit O. And the reason, and it's a symplectic space, and the reason why it's symplectic, because in this case, the quotienting by G coincide with taking the symplectic quotient, symplectic reduction of this quasi-tropic subspace in M. And so, what the Hamiltonian reduction does is it gives us a symplectic stratified space, which is a symplectic stratified leaf in the stratified Poisson space M mod G. So now this is a section on representation theory. So I should explain how all this is related to representation theory. So digression, integrable systems and representation theory. So yesterday Igor Frenkel gave a very nice kind of philosophical talk about the perspective of representation theory. Well, he is sort of my senior comrade in some sense. We wrote a beautiful paper together, I think. So, so I should follow the trend. So initially I didn't plan to do this, but now I cannot avoid it. So digression, how the integrable systems are related to representation theory, and in more generally, how Poisson geometry is related to representation theory. This is not a collection of theorems. This is sort of a mind frame, which I think it's better to have when you do either representation theory or Poisson geometry, because these are the two sides of the same coin. So, and kind of there are two sides of the same coin, and in between there is a metal, and the metal is here. It's the way how they are connected. This is the most difficult part. So classical Hamiltonian systems and quantum integrable systems, and in general, here is the classical Hamiltonian, meaning the Poisson geometry, symplectic geometry, everything from that realm. Here you have quantum, meaning associative algebras, representation theory, and everything algebraic. So what's the relation? So we have associative algebras. An example of an associative algebra is the universal enveloping algebra of a finite dimensional Lie algebra. And then on this side, we have the dual space to the Lie algebra G, which is a Poisson space with the Lie-Kirillov constant Poisson structure. Functions on this space is a Poisson algebra, and the relation between these two is the deformation quantization of Poisson algebras. This way you get families of associative algebras. Now, irreducible representations of algebras, well, their counterpart is geometric quantization. Their counterpart is symplectic leaves of Poisson spaces. So, for example, in this example with the Lie algebra, these are coadjoint orbits. And the connection between these two subjects is geometric quantization. So geometric quantization gives you a vector space, and the difficult part is to show that geometric quantization actually gives you a representation, which is still the subject of serious research. So, but conceptually, that's what you should expect, and that's how it works. So then a quantum integrable system, kind of heuristically, you can think of a maximal commutative subalgebra in some associative algebra. And of course, you have to be careful kind of to be more precise here. Say, for example, if you have the algebra of differential operators on an n-dimensional manifold, then the quantum integrable system in this algebra is, say, subalgebra generated by n independent differential operators. And then so on. You have to kind of be a little bit more careful here, but since it's a kind of bird's view on the subject, so I'm not careful here. So here, an integrable system is a maximal Poisson commutative subalgebra. Also, one has to be careful here a little bit. So, and the relation between these two is, again, some kind of deformation quantization. So here is an example that demonstrates what is the quantum analog of Hamiltonian reduction. So let's consider the Hamiltonian reduction in the very simple case. You have a finite dimensional simple Lie algebra, and you have a finite dimensional Lie subalgebra, and you have the corresponding Lie groups, and G and K is a subgroup. So then on the left, you have irreducible representations of G. On the right, you have coadjoint orbits in G star. So on the left, you have, with each representation, you associate natural algebra. That's the algebra of endomorphisms of this irreducible space, the matrix algebra. In this matrix algebra, you have a natural subalgebra of k-invariant operators. So that's the counterpart of this is you have the algebra of all functions on the orbit, and then in this algebra you have the subalgebra of k-invariant functions. So then you can restrict this representation to a representation of k, and then let's assume that G and K are simple. So then your representation decomposes into the direct sum of K modules, reducible K modules, and some multiplicity spaces. And supposedly, this is what you should obtain if you will consider K orbits inside of this coadjoint G orbit. If you construct geometric quantization of this coadjoint orbit, then with some careful geometric manipulation, you should be able to obtain this. I don't know if anyone actually managed to do this. So, but again, let's take this square of this decomposition. Let's consider K invariant endomorphisms of this vector space. According to this decomposition and the Schur lemma, this space is isomorphic to the direct sum of endomorphism spaces of these multiplicity spaces. And that's a geometric quantization of k-invariant functions on the coadjoint orbit. So now, if you just take one of the components here, that will be exactly the deformation quantization of the space of the Hamiltonian reduction. So picking up pre-image of the coadjoint orbit of K is equivalent to picking up the irreducible representation of K. And so, kind of again, heuristically, you have this space, which is the space of functions on this quotient space. You just have to be careful with which quotient space you want to take. But again, since this is a kind of philosophical discussion, that's the kind of what we have. So this is how all these spaces that I will be talking about, how they are related to representation theory. If you will try to quantize the results that I will be talking about, you will have some statements from representation theory about multiplicities. And actually, this observation is very useful if you want to study kind of geometric asymptotics of these spaces. Say when the highest weight goes to infinity, when the highest weight goes to infinity and this highest weight I goes to infinity, some kind of asymptotical representation theory in the style of Virchow when you consider large algebras and large representations. So let's go back to the Earth and let's focus on the Hamiltonian reduction. So now I want to talk about very specific integrable systems, Calogero-Moser and spin Calogero-Moser. And I want to demonstrate that in these systems where everything is known, still there is some curious result related to the stratified structure of these systems. So first, let me define spin Calogero-Moser systems. So let G be a simple compact Lie group. It's not necessary that it's compact, but let's just assume for simplicity. Consider the cotangent bundle on G. Let's trivialize it by right translations. So then it's isomorphic to G star cross G. So G acts on itself. There are three actions: left, right, and their composition, the action by conjugation. So all of these actions can be lifted to the action on the cotangent bundle. After this trivialization by right translations, the group element G acting on the pair X, H, X in the dual space to the Lie algebra, H in the group. So the action is, left action is this. right action is trivial on X, because we used it for the trivialization of the cotangent bundle. And then the adjoint action is just this. This is the adjoint action of H. So how much time do I have? 30 minutes. So I think I have enough time to tell a story. It's a story not related to mathematics at all, but it's related to, it's a sort of apology story that maybe if I'll have some mistakes here, that explains it. There is a very nice autobiography of the artist painter Dali, where he explains how his friends from Paris are visiting him in Spain. And he saw them coming to the house, and then he has a white shirt. He thought, no, this is, for the artist, it's not good. So he put some paints on it, so cut some sleeves, and then look, he said, no, this is too ridiculous. And he goes back to the white shirt. So that's more or less how I was writing these slides. So you don't want to see what was there in the middle. So unfortunately, some of these mistakes remain. So the left moment map is just a projection to X. The right moment map is the kind of projection to X twisted by the coadjoint action of G inverse. And the moment map for the adjoint action is just the sum of these moment maps. So it's X minus the coadjoint action of G inverse on X. So this quotient space is a stratified Poisson space. It's very trivial how you can kind of describe this space. Well, G is compact. Think of SUN. So by conjugations, you can diagonalize group elements. Then there will be stabilizer in the Cartan. It will act on G star. But then it all depends on whether you choose the regular element or there are some eigenvalues that coincide. So then there will be non-trivial stabilizers, so you will have a natural stratification of this. Symplectic leaves, that's a Hamiltonian reduction with respect to coadjoint orbits in G star. And such symplectic leaf is simply the set of all elements in G star cross G that satisfy this property that the moment map of X is in the orbit, and then you quotient by G. And that's for SUN, this is a matrix condition on this pair X and G. So, so now I want to describe the spin Calogero-Moser Sutherland integrable systems via the Hamiltonian reduction of T star G. It's in the spirit of the paper by Kazhdan, Kost and Sternberg, where they did it for the cotangent bundle of the Lie algebra. And their aim was specifically non-spin Calogero-Moser system. But the philosophy is more or less identical, so I think it's natural to give this reference. So let's look at the cotangent bundle. So we have a natural G invariant Poisson projection, just projection to the first factor. So it defines the Poisson projection from this quotient space, which is a Poisson space. Poisson, I want to say Poisson manifold, but it's not manifold. It's a stratified Poisson space. So it projects to G star mod G. Now this has non-trivial, G star has non-trivial Poisson structure, but the quotient space is trivial. It's isomorphic to the dual space to the Cartan by the Weil group. And then the restriction to the symplectic leaf of this space gives the mapping from the symplectic leaf to this stratified space H star mod W. H star mod W, it looks like a cone. So there is a natural stratification. So of the inside of the principal vial chamber, the inside of this cone, and the walls and the origin. So, and the Poisson commutative algebra. So you take the pullback of functions on the base, and this gives you Poisson commutative subalgebra in the algebra of functions. So in particular, these functions are restricted to the symplectic leaf give polynomial functions from this subalgebra, and they are Poisson commuting, independent, and they generate the whole subalgebra. So now, so this is the total projection that we constructed, but it can go through the intermediate Poisson manifold. We can take G star cross G star, fiber it over G star mod G. And I must say that this, well, there are some technical details, but I'll just sweep them under the rug. So if you take mod G, then, so these two arrows is the projection to the first factor and the projection to the second factor. If you take the quotient over G, these projections coincide, and you have the projection of Poisson spaces. Now, if you take the symplectic leaf of T star G mod G, so then you have the projection to some subspace in here, and to some subspace in G star mod G. And that's a super integrable system. Super integrable system because you can check that the dimension of this is full dimension of G star mod G, is the rank, but this is not G star mod G. And it's not the principal vial chamber. It's some kind of shifted principal vial chamber. So, as we will see. So, so I made this observation in 2002 that it's a super integrable system, and it coincides with the spin Calogero-Moser Sutherland system. There is, if I'll say Calogero-Moser here, it means Calogero-Moser Sutherland, because Calogero-Moser they did it for the rational case, for the case of the cotangent bundle to the Lie algebra. So this then Sutherland generalized it to cotangent bundle to the Lie group. So so this, for superintegrability, it's very important that the dimension of this Poisson manifold plus the dimension of B is equal to the total dimension, because it's a necessary condition to the fact that fibers of the last projection are symplectic leaves in P. So anyway, so I proved that this is all true for the maximal stratum, but this question was still bugging me. What is happening for the other stratum? What's happening globally? And so finally, with I keep mixing up. So actually, Chengzhou is not Chengzhou; he's Zhucheng. So so Zhucheng, Kaijiang, and Hussein Xiao. So with them, we sorted out this case for SUN. So I'll present what's happening for SU3. So in this case, let's denote by OXC is the coadjoint orbit through the element Xi in the Cartan subalgebra of SU3. So Xi is this let's forget about I. So you can think Xi as a diagonal matrix with the diagonal entries A, B, C, such that it's a traceless matrix, and we choose a representative of the Weyl orbits. So we assume that they are ordered as SU, so they are real. So then this is the space of such vectors in R2. So it's the usual picture for SUCs. You have the root system, you have fundamental weights, and then this is the principal Weyl chamber. And you can see that this space is stratified. So there is an inside of the Weyl chamber which is two-dimensional. There are walls, these are one-dimensional. There is an origin that's zero-dimensional. And so for ABC, there are four natural non-trivial choices, trivial choices in the origin. So one is generic position, the other is on one wall or the other wall, and the third one, there is a special direction inside of the principal Weyl chamber which is invariant with respect to one reflection of the Weyl group. It's the direction of another root of alpha 1 plus alpha 2. So I'll just use the notation SC for the symplectic leaf corresponding to this orbit. And now let's look at these symplectic leaves. I just want to remind you that these are symplectic leaves in the T star SU3 mod SU3. So first, if this is a rank 1 orbit, either omega 1, C omega 1 or passing through C omega 1 or through C omega 2. So in this case, C is actually this. So then that's the definition of symplectic leaf. But then if you solve this this moment map equations, so you will see that this symplectic leaf is just isomorphic to T star of the regular part of the Cartan modulo the action of the Weyl group. And basically these are the representatives of these pairs. So it's a smooth orbifold. So if you don't pay attention to the quotient by S3, it's a smooth manifold. And we have a Liouville integrable system, the projection from S to B. So it's generated by, it comes from the projection X gamma to X. So B is a region in H star mod W. There are two independent Poisson commuting Hamiltonians, trace of X squared and trace of X cubed. So this is a very familiar Calogero-Moser-Sutherland system, which describes three particles on R. This is the kinetic part of the Hamiltonian. This is the interaction. C is an arbitrary real number. It's the quantum case. This is a classical case. So you can see that if you start from a regular point, first of all, you can see that Qi cannot be equal to Qj because the Hamiltonian would be infinite. And if you start from some regular point, the trajectory cannot move to the singular point, to the collision point, because otherwise the Hamiltonian will not be conserved. So we don't have collision points, and then it's not difficult to check that B actually looks like this. This is the principal Weyl chamber, and it's not possible to have all values in the Weyl chamber. You have to shift it by C, and that's our B. So here you have two-dimensional Liouville tori, one-dimensional, and fixed point. Fixed point. So I know that there are some physicists here, just from kind of usual old-fashioned physical intuition. What would you assume, what would you suggest for the fixed point of the evolution? You have 3 points on a circle. Which configuration would give a fixed point? Yeah, when they form a triangle, exactly, equilateral triangle. So yes, so that's the fixed point. And then the one-dimensional trajectories are kind of less trivial. But if you look at this picture and imagine that 2 is equal to infinity. So you have this infinite dimensional space of generic solutions. And then you have some kind of finite dimensional strata of this in this space. So then you naturally would say, oh, it's reminiscent to the space of solutions to nonlinear integrable partial differential equations. So you have all kind of generic solutions, nothing special, but then among these generic solutions, you have soliton solutions, which are stratified. So you have 1 soliton, 2 solitons, 3 solitons, and so you have all these subspaces in the infinite space of solutions. This is actually very similar. You can call this kind of soliton subspaces. So now let's move to, so we looked at the wobbles. Now let's look at generic points. So now ABC is in the interior of the Weyl chamber, but they are not on this central line. That's the direction of the third root. So then it's not difficult to show that as C, again, it's a smooth orbifold. So it's isomorphic now to T star H regular, but now here there is an extra factor. It's the Hamiltonian reduction of the coadjoint orbit with respect to the action of the Cartan. The coadjoint action is Hamiltonian. Cartan is a subgroup, so Cartan also acts by Hamiltonian mappings on the dual space to the Lie algebra. The Weyl group S3 doesn't act on there is no canonical action of the Weyl group on the coadjoint orbit. There is a canonical action of G on the coadjoint orbit. And in the group, there is a natural subgroup, the normalizer of the Cartan. So the normalizer of the Cartan acts on the coadjoint orbit. But because we quotient by H, so this action of the normalizer actually becomes the action of the quotient of the normalizer by the normal subgroup Cartan. And that's why the Weyl group acts on this quotient, on this Hamiltonian reduction. And so this is a smooth space, and that's a smooth orbifold. So that's the regular Cartan. That's the Hamiltonian reduction of the coadjoint orbit with respect to the action of the Cartan. And you can see that it's a kind of sphere intersecting with some kind of funny condition. But this funny condition is very important. It tells us that Zij cannot be 0 because neither A, nor B, nor C are 0. So it means that Zij is not 0. And now this construction that I explained before, from T star G to to this G star over G star mod G to G star mod G. It gives a super integrable system when you restrict it to a symplectic leaf. This symplectic leaf is 6-dimensional. It's very easy to see that it's 6-dimensional because so here we have 4 and here we have 2 dimensions. So it's a super integrable system in the sense that the image of the symplectic leaf in this Poisson space is 4-dimensional, and then the base is 2-dimensional. Again, there are 2 independent Poisson commuting Hamiltonians. These are two independent functions on the base, trace x squared and trace x cubed. This is our spin Hamiltonian. So kind of if you can imagine z are kind of spin variables, and then p and q are positions of these three particles. And again, there is a simple observation that collisions are impossible because for the same reasons, because Zij cannot be zero. Collisions are possible only if the numerator will vanish. So here there are no collisions. So here you have the variables Zij, they move when you consider the dynamics. And in the previous case, you don't have the Zij variables. This is a constant, fixed by the choice of the orbit. So the phase space here is 4-dimensional. And the phase space in the spin Calogero-Moser is 6-dimensional. Two extra dimensions, they come from this Z variables. Z variables, it's this. These are the, it's this Z. So sorry, it's this Z. So it's Z that enters into the moment map equation. So this space is 2-dimensional. Yeah. And then there are no collision points, and then you do some computation which is not too complicated but also non-trivial, and then you discover that the base of this vibration, so possible values of classical integrals H2 and H3, they are given by the shifted, again, by the shifted principal Weil chamber, but it's shifted asymmetrically. Before it was just shifted by C and C, now it's by B and C. And so we expect that this is the same for SUN. It's working. Dynamical, they move, yes. No, 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 no. No, you see, that's what is written here. So this is P, Q, and this is Z. So there are, in the Calogero-Moser case, the phase space is 4-dimensional. Here it's 6-dimensional. Sorry? It's complicated. I mean, I can write it, but maybe after the lecture. So so these are extra spin variables. So you have spinless Calogero-Moser where there is only P and Q, and then you have spin Calogero-Moser where there are P, Q, and Z. Z are the spin variables. I mean, they are not usual spins. They are not SU2 spins. In this sense, maybe the name is confusing, but they're kind of classical isospins, maybe better to say. Classical, of course. Yeah, everything is classical here. So, okay. So this is what happens for the generic orbit. And now for the special orbit of this type, so in this case, actually, the symplectic leaf symplectic leaves corresponding to these orbits, they are naturally stratified by this orbit type, by this Schmarr-Lerman stratification. So there are two strata, maximal and minimal, with respect to the size of the stabilizer. How much time? 5 minutes? Okay. So I should skip some of the details. They are beautiful details, but they are details. So here's the structure of the trajectories in this case. So every trajectory has a regular point. A regular point meaning Qi is not equal to Qj. So we can start from the regular point, any trajectory. So now suppose that we started in the regular point, then there are three possibilities. Basically all kind of reasonable possibilities. First, the trajectory may avoid all collision points. It depends on the initial condition. It may have one collision point where Qi is equal to Qj. It's possible because the numerator can vanish, this Zij. And then it's possible that there are two collision points. So which means that we have this more refined stratification of these two strata into regular points and irregular points. And actually the trajectory, you see, the Hamiltonian flows cannot leave this orbit type strata. So they always stay within. But with this extra stratification, it can go to the boundary, can stay there a little bit, and then can go back. Or it can cross the boundary, move in the irregular part, and then come back. So this is the new phenomenon. So it turns out that it's possible. So and the same is happening for the multi-time evolution, because you see, mathematically it's a little bit misleading to choose a specific function and to consider the Hamiltonian evolution of this specific function in an integrable system. In an integrable system, you have to choose all possible integrals and consider multi-time flow. So something interesting also happens for the multi-time flow, but I only have 5 minutes. So then we can consider SUN system and spinless SUN system, interesting enough. And this is a work with Andrei Leshik, Gurey Ma, and Ivan Sechin. So then I will skip all this since there is only 5 minutes. And just, so this is the example that we already had for the SU3. Yes, so in the SUN case, it's very similar. You just have to take the principal Weil chamber and shift it in the direction that's, the principal direction that's proportional to C. And you will have the base of this vibration. And because the base is stratified, because it's a cone, it's a principal Weil chamber, so the total space have induced stratification because we projected to stratified space. So there are pre-images. And these pre-images are low-dimensional Liouville tori. Okay, and the pre-image of the origin is the fixed point. The pre-image of every stratum gives some low-dimensional Liouville tori. So that's an example of a nice and simple stratification when you big dimensional tori, when you go to low dimensional strata, they just shrink. And in the extreme case, they become just a circle. So concluding remarks, yeah, I already said that these are the analogs of solitons in integrable PDEs. So actually, for compact Lie groups, when you start to go into these details, you can see some beautiful features of coadjoint orbits and all these constructions that you can do with coadjoint orbits. So then it's actually, I didn't find any discussion in the literature of such things. Kind of deep, detailed discussion. So then there is something that's called action angle duality. You see, T star G, you can, once you trivialize it, you can project to G star, or you can project to G. If you project to G star, you will have all these Calogero-Moser type systems. If you project to G, you will have Ruijsenaars type systems. And there is a duality between these systems when you replace the action and angle variables. So it would, I think, one of the coming projects is to see how exactly this duality works for in the stratified case, how low dimensional strata intersect. Of course, then there are integrable systems related to moduli spaces of flat connections. So there are two types. There is a type of by Hitchin, constructed by Hitchin, and then another type is sort of more related to TQFT and to modular tensor categories. It's the one that constructed by Artamonov and myself a few years ago. So in this, so basically what they would give is you have two copies of G, say for the torus, you have two copies of G, the holonomy along the A cycle, along the B cycle, and then you mod G, so you have two natural projections to G mod G, G mod G. So this is some kind of relativistic Ruijsenaars system and it's dual. And the duality is given by the modular group action. So all this is more or less well known, but the stratification was not really studied, I think. When you start to quantize these systems, the, the quantum analog of this one-dimensional strata on the base, these are the infinite sequences of spectral points of quantum Hamiltonians, where instead of two independent Hamiltonians, two independent differential operators, they become dependent with the coefficients that don't depend on the point of the spectrum. So inside Hamiltonians you have two independent differential operators. On these lines, you have, on these infinite sequences, you have algebraic dependence between Hamiltonians. So then there is something that's called hybrid dynamics. I think I'm running out of time, right? Okay. So hybrid dynamics is the work that we did with Leszek and Sechin. It's like a system, it's like a control system. You have a classical Hamiltonian dynamics on the base, quantum Hamiltonian dynamics on the fiber, and classical dynamics control the quantum dynamics. There is no feedback. So it's just, usually it's in the control systems. So interestingly enough, you can construct also Hamiltonian, these double layered Hamiltonian systems where you have low Hamiltonian system controlling the upper Hamiltonian system, but there is no feedback. That's it. It's also related to stratification. And then there are so many of these things. Thank you.
Okay, so it's time for questions.
Do you have a quantization of the spin Calogero-Moser Hamiltonian?
Yeah.
So what is, because I mean, as you said, for the usual Calogero-Moser, you just replace c squared by c squared minus 1 over 4. And so what do you do here with these z variables?
So basically what you have to do is instead of the coadjoint orbit with the z variables, you have to choose a representation of G. And yeah, I don't know how much I can give a lecture about this, but I don't know if I have enough time. It's a very broad question. So the short answer is that there is something that's called quantum spin Kalogero-Moser systems. There are several versions, and
so there is no uniqueness. You have to, you can choose, you can do this or that, or
there is no uniqueness. If you choose an irreducible representation, you can choose 2-dimensional, 3-dimensional, 4-dimensional. In this sense, there is no uniqueness. Yeah.
So, any other questions?
You can also consider elliptic Kalogero.
Absolutely.
So, and this is also can be obtained from Hamiltonian reduction.
No, it's a different story. I mean,
so you can consider loop group.
Yes, yes. I didn't mention this at all because it's like it's like the other universe. So there is a Milky Way. There is sort of our side of the Milky Way, and then there is the other side. It's on the other side. It's so it's the you see when you consider T star G, you trivialize it to this. For all our purposes, it's the same as G cross G because G is simple, and as we know from Professor Lustig's talk, then the most beautiful mathematical paper in the universe is the paper by Killing, and there is a Killing form on G, and I believe that Killing invented everything except for the Killing form, and Killing form was invented by Cartan. So this is why we have the isomorphism, and then if you take a special subspace in the loop group, that's U is the loop parameter. So this and this, that looks like T star G, and so actually there is another way to think about all this in terms of loop group. But that's just another 2 or 3 hours of talking. So the short answer is yes. There is an elliptic version. It's well known. The classical elliptic version was, I believe, was invented by Krichever, Babylon, and 2 other people. There is a whole story for the elliptic case. It's more complicated. Again, there are some real forms. And for special real forms, there is an analog of this stratified story. Are you satisfied? No?
But I'm talking about reduction of the loop group and obtaining elliptic Kalogero-Moser.
I think to obtain elliptic Kalogero-Moser, you don't need reduction. That's the elliptic story, I think.
But it can be done.
Hmm?
But it can be done.
It can be done, yes, but well, anyway. Igor, I think you know the answer to this question. Okay. So, sorry,
Okay, so we have run over time, so let's thank our speaker again.